Hi students, this is Mr. Epperson and welcome to a self-guided lecture on temperature and heat. Temperature and heat are kind of a funny topic to talk about because in most senses it's a term that we throw around, both terms, we throw them around all the time. You know, something has a lot of heat or feels hot. Or, you know, we might just say, what's the temperature today? And we think we know what we're talking about. But in science, and especially in chemistry, it's important that we're specific about what we mean, because these are measurable quantities and actually point to a greater reality. So one example I like to show students is this gentleman here who, as you'll see in the video, is able to manipulate the effects of heat and temperature to still be able to amazingly slap molten rock. What you're seeing there is liquefied rock basically being, I'll show it again, being touched by human hands, right? That's probably about 900 degrees Celsius. And that molten metal is just somehow not burning this guy's hand. Pizza ovens, by the way, are around 400 degrees centigrade. So you're not used to the centigrade scale. It's several thousands of Fahrenheit, degrees Fahrenheit. So how is this possible? How is this guy able to do that? Well, that has basically goes back to the idea of what is heat, actually. What is heat as an entity? So this was actually a question that a lot of initial chemists had, and this gentleman named Antoine Lavoisier, he has some interesting chemical ideas and things that we're very grateful for. This was his idea, though, on heat, and he proposed this around 1770. So he proposed this idea called the caloric theory. Now, it might sound like some kind of dieting program, but their idea of caloric was that they were naming this substance, basically a substance that they called a subtle fluid, and it had a mass to it and matter. It was a thing that flowed in and out of objects that had heat. So this might sound kind of weird, but if you think about it, if I put my hands on my laptop right now, I'm in a cold garage and my hands are a little chilly, and if I feel my laptop, I feel that it's hot. You know, it's working hard and it's running lots of programs. So it's working hard and it's hot. So I'm getting some heat into my hands. And it would make sense for somebody to say, well, what is that? Why are your hands hot? And without any other ideas that might have been influencing that, it might still seem strange, but maybe not. You know, my hands have just absorbed some of this caloric energy. And that's what they called it. That you absorbed caloric. So something that was hot had caloric, and something that was cold had less or none of it. And you just thought of it like a fluid. So something that flowed into your hand or into an object. And if it lost it, right, my hands will later cool down, it would go into the air. And so there was a very good explanation for how this worked, but it had problems, right? Like I could actually get my hands warm by rubbing them together, right? If I rub my hands together, I can create heat, energy. And if they didn't have caloric to start with, that idea started to fall apart. So later on, some of the ideas about how energy worked and how particles worked and objects worked kind of started to influence how we thought about heat. So you're seeing here a little animation of basically the states of matter. And we'll go into this a little more in depth, but the different states of matter are basically gas, a liquid, and solid. And you're very familiar with that idea, I'm sure, but how about the particle nature? Well, heat is a measure of energy due to particle nature of different types of the particles that are in different objects. So let's just use, for example, like water. A solid bit of water, like ice, would have particles in it, and then if you heated that up, you'd get liquid, and then if you heated that up even more, you'd get steam. And those are the different phases of water. Now, the different particles are moving at different speeds, if they are hot or if they are cold. And you can see the gas particles here moving very quickly, the liquid moving about just a little bit, and the solid kind of staying there. But because they are particles and they tend to have some energy to them, they are still moving a little bit. So this is called the particle nature of matter. And fast-moving particles have lots of heat, or they have lots of, we might actually better be called thermal energy or kinetic energy. And these molecules have a lot of energy to move. So if something can move energy from itself to something else, we'll call that transfer heat. So that's what heat is. It's the transfer of energy. And a slow-moving particle then would have less of that kinetic energy. It might be better than saying have less heat, have less kinetic energy. Probably should have changed that. So heat is really defined as a flow of energy from hot to cold. So slow-moving particles have less kinetic energy. Fast-moving particles have lots of kinetic energy. And when they hit each other, we call that transfer heat. Here's kind of like an example of that, because it never moves from cold to hot. And let's see kind of why that might be the case. Well, when we look at a little animation here, we see actually a couple things going on here, but let's point out one thing. We see that some of the different particles are hitting each other. And when they hit each other, you might see a fast-moving particle. Maybe let's pull out one here. Okay, let's look at that one. Here's a very slow-moving particle right here, and a fast-moving particle right here. And when they collide, you see that the slower-moving particle starts to speed up, and that faster-moving particle slows down a bit. And that's the transfer of heat. That's what we might call one got hotter and one got colder. And that's really the best way of understanding heat, temperature, and thermal energy. Something having some kind of motion to it, and this really being what they were looking for when they came up with that idea of the caloric substance. It wasn't another substance, it was the thing that you were dealing with. It was your hands themselves. It was the computer itself having that energy in it by the particles themselves moving rather quickly, and then those particles themselves transferring their energy to another substance. So this gets us to the idea of temperature. So what is temperature then? Temperature is basically reading an average of all those motions of all the different particles. So if you're thinking of like a thermometer, if I put a thermometer in a vial here, it's reading the kinetic energy of those particles, but it can't be reading just the energy of one. There's, many billions of particles in that sample right here of water, whatever it is. Maybe a strange yellow liquid. But you've got all those particles moving about. Some are going real fast, knocking into that thermometer and heating it up a bit. And some are moving a little slower and actually taking energy away from the thermometer itself. And the thermometer then adjusts based on all those different motions to give you an average idea of how fast the average particle is moving. So let's look at some animations that'll give us an idea of this. So the first one over here is showing us all the different particles moving about as you increase the temperature. And I know it's hidden a little bit, but that's okay. Just watch as the temperature increases as the total particle movement increases. So you can see the thermometer is going up, but it's not measuring any one particle. It's measuring all of the particles together will give you an average number. So that's an idea of how temperature is actually measured. It's the motion of all the particles together. How about looking at it if you have a structured system, like with some order in it, hot liquids on one side and cold on the other. And when then we would then withdraw a barrier separating the two, and you'll see them balance out. So if you'll mix hot water and cold water together, pour them together, what you're doing is you're actually taking the energy from the hot water and transferring it to the cold water. And the answer of, I've got 50 degrees C water and 10 degrees C water. If I pour those together, I'm going to get an average temperature of the two, which is right in the middle, 30. Middle of 10 and 50 is 30. So I could very easily predict what my final temperature will be of one object and another, and when I add them together, if I understand this principle. And this turns out to be true. So then how does this guy actually beat the temperature and the heat odds by slapping metal and not getting burned? So how does this work? Well, if we understand average kinetic energy and kinetic motion as what defines temperature, in human flesh burning at, I don't know, 130 degrees Fahrenheit, something like that. It's what a raw steak is at, so I'd assume it's about the same. He's gonna be able to avoid keeping his skin at that below that level by moving through a very hot substance very quickly. And you can actually simulate this if you move through something like a candle very quickly with your finger. I don't know if you've ever done this, but just be careful. But I don't have a candle here. I have a lighter, kind of like a torch that I use. Sometimes I'll use this for chemistry demonstrations, and this, I can get a flame going here. It's pretty hot, but it will not burn me even if I've dragged my finger through here, so long as I keep that average temperature down. If I go faster or drag through here slower, it's going to start to hurt, and I can kind of feel that was getting pretty hot and a little uncomfortable. So that is the way that temperature and heat can be understood. Again, temperature is an average. So I hope that was helpful.